Thank you for the great introduction. Thank you very much. Thank you, Andrea. I had a great day today, and actually this is the first time I'm really in Berkeley, because before I was only at bars. So I'm really glad I had great conversations with some of you. And yeah, so today I want to talk to you a little bit about the thoughts I have on uncertainty in robot manipulation. So basically that's the main area I've been working on, robot manipulation. Particularly interested, or of interest to me, is anything that comes with visual and tactile sensing and how a robot can make decisions based on that messy data. And really my research is driven by the puzzle of why humans are actually so amazing at manipulating any kinds of objects while it's so incredibly hard to make it work on an actual robot. And we don't know yet how, and it's just a very intriguing puzzle for me. And I'm really wondering what's the ingredient to that magic sauce that makes us humans, and that will finally enable robotic manipulation to reach a level where they can actually be helpful to humans. That's, by the way, the Apollo robot, which I worked on at MPI, which I miss dearly. It had to stay in Germany, unfortunately. So today, I have a bunch of different thoughts, obviously, about what could make robotic manipulation reach the levels of human manipulation capabilities. But today I want to focus on this one point, which is on bracing uncertainty. So what do I mean by this? What I mean by this is, let me circle back a little bit and talk about maybe what I don't mean by this. So what I noticed in computer vision research and also in machine learning research is that there is a lot of focus on making a visual task or a prediction task as precise as possible in terms of accuracy. And in computer vision, that's preferably maybe a per pixel segmentation over the entire image, or maybe a point in a point cloud, or maybe you want to predict every single thing that's going to happen at a very far distant point in time. And so I'm realizing that especially computer vision and ML right now are very obsessed with accuracy, and that's of course a very interesting and extremely challenging problem. But I also want to say that maybe we will never achieve perfect accuracy, and if we accept that premise, that we will never achieve it, then I think one way to look at it is that we actually have to think about how we deal with always having a certain base level of error and uncertainty. I think that actually accuracy is not necessarily what a robot only needs, at least, or a high level of it. So, for example, think about really what we are interested in robotics is success at a certain task, or maybe at a range of tasks. So if you look at this kid here, maybe playing with these toys, like the way you imagine is like this kid is probably picking things up, trying to assemble them, trying to put that little puppet into whatever here or here, and things are going to slip out of his or her hand. This kid will just be able to pick it up again and correct to whatever error it's going to make, right? And so really, that kind of fumbling around with all these different objects is actually allowed. It's, if we would see a robot that can do that kind of playing with these toys, we would be amazed, right? There's no robot that can really do this. And I think that if we are interested in this kind of task success and being able to actually correct for errors, then we may not be actually, I don't think that we actually need a very high accuracy for this, because just having accuracy doesn't necessarily imply success at a particular manipulation task. So therefore, I would suggest that maybe just accuracy is not the right goal to strive for in robotics, but rather maybe we should strive for methods that can just accept the premise that there will always be uncertainty, and then once we accepted that, think about how we can develop methods that can continuously replan, for example, and correct for errors. So what we kind of have to do in robotics is to close these fast feedback loops where we basically close a control loop around very messy, high-dimensional sensory data that helps us to interpret the scene and make decision. And that actually needs to happen very fast. And in order to make good decisions, we may not need total accuracy, but rather some way to plan ahead, try things, get fast feedback, figure out if it actually happens, and then potentially replan, right? So I don't think we need to actually plan everything out, but I think there should be like a methods that allow these kind of fast feedback loops to run, and then maybe some learning and planning around it that can be redone. So of course, if we accept this, there are still a lot of challenges. We still have to ask the question of like, okay, so what are the important information that we need for a particular task? And how off can we be, or how much inaccuracy can we actually accept? But one message that I just want to leave in this room, I think if you work on a real robot, you have to really say goodbye to perfectionism and total accuracy, especially in perception and prediction. And if you want to come to robotics, you really have to embrace this kind of chaos and accept the fact that everything is uncertain. And so now that we, maybe I hope you too, accepted this premise, we can work on controllers and reactive planners that can continuously adjust. So to kind of give you a few examples of how I think about this, I'm going to talk about 3 of our works that in different ways deal with uncertainty in this way. Instead of trying to reduce it even further actively through learning perception or prediction models, they do that slightly differently. So I'm going to talk about one project that tries to actually place optimally certain fixtures in the environment so that manipulation tasks become easy for the robot. And the challenge here is to figure out like how to automatically learn how to place these fixtures that funnel uncertainty without necessarily needing more accuracy and perception. A second project that I'm going to talk about is on task and motion planning, where the uncertainty really comes from a scene that is changing in non-predictable ways. And we want to find a way to do task and motion planning such that it's still adaptive to these dynamic scenes. And then I'm also going to talk about a project that is on manipulating deformable objects, which is very hard because it's a high-dimensional state space. There's a lot of uncertainty coming from perceiving this state and also in predicting the dynamics of this object. All right, so these are the 3 projects I'm going to talk about. I hopefully managed to cover today. Let's start with the first one that is on scaffolding manipulation skill learning. So first I'm going to show you these 3 different tasks that we actually considered: peg insertion, turning a wrench, and doing this shallow depth insertion. It's like a robot actually inserting the battery into your phone, for example. And it's really challenging to learn these tasks, right? I mean, you can do it with maybe a deep RL approach or whatever, but you will need many, many, many samples to actually be able to learn this. What we think about actually, one way to approach this is not to try to come up with better perception models or try to come up with better maybe model-based prediction method, but we somehow sidestep this issue and ask ourselves, okay, can we actually place physical scaffolds in the environment and find out how to do this optimally to help this robot to learn faster? And this is actually a task that people have figured out a lot. So one is, for example, just think about how people build buildings. They use scaffolds to temporarily support material and get access to heights and axes. Some parents use training wheels to teach their kids how to actually ride a bike. And then in industry, it's also pretty common to have fixtures in the environment to reduce uncertainty in this manipulation task. So our goal here in this project was really a framework for a robot to autonomously discover how to place these kind of scaffolds or how to help one robot by scaffolding to learn manipulation skills easier. So take the peg insertion task as an example, right? it's a difficult problem to actually smoothly insert basically the peg here, right? Because you have to kind of figure out the right direction. It's like very low tolerance actually. But if you have now one robot that places a fixture here, then basically that really funnels the uncertainty that you may have from perception, and this other robot will just not be able to slip out of this perfect positioning, right? And of course now the question is, how does this robot figure out what the optimal positioning actually is? Right? And so the way we approach this problem is by having an inner and an outer learning loop. So in the inner loop, you have this particular robot trying to learn to do this manipulation task, right? So it's getting this RGB image, and it tries to learn a policy for choosing the next best action. And it has, this is the particular learning curve, okay? And then on the outer loop, we have basically this robot trying to figure out, okay, how do I help this robot to learn this better by placing this fixture? It sees this depth image, and once it places the fixture in a certain way, this robot will try to learn it and will give the outer loop a reward on how fast it actually learned that. So the inner loop is actually not so interesting. We just use an off-the-shelf RL method. It's not so important. What is actually more interesting is how we formulated the outer loop. And we just framed this as a contextual bandit, where basically the context comes from this particular depth image that the robot sees. And then the robot has to basically make a decision on how to place the the fixture such that the reward is maximized. And reward maximization here means that this robot learns faster, right? Okay, so how does this exactly look like? So we have this as the context. Then this robot can like do all these different positions of the fixture and gets a particular reward from how fast the other robot learns. And the challenge here, the algorithmic challenge here is really that this Q function that the outer robot tries to learn, which looks like this basically. So the context, this is the context or the current state, and this is the action of how it places the fixture. That particular Q function is actually discontinuous. Okay, so this is visualized in a simple way here, where you have basically the context here, and as if this fixture basically covers the whole, the other robot will never learn, right? So the Q function will basically give you a low reward. If it's exactly at the right place, this fixture, you will get the maximum reward because it will learn actually very fast. And if the fixture is slightly shifted, this will still become harder for the other robot to figure this out, right? So that's really the challenge here. And the way we, what we propose here to solve this is basically an algorithm that combines a zooming algorithm for learning a continuous reward function and a smooth algorithm to deal with the discontinuous reward function. So I just want to run you through this algorithm, which is very complex, but basically what we do is we initialize a bunch of bandit arms on this action space, and then for each of these bandits, we basically sample a particular action. We execute that action and get a reward. So our other robot learns at a particular speed. And then we figure out, like, okay, what's the mean reward over all the trials that we have done? And that's basically the value that we have for this Q function. And also, if some of the action space is actually not covered, we introduce new arms for the bandit. Okay? So that's the algorithm that we propose for this problem where we have this discontinuous Q function. And okay, so what did we achieve, right? That's a question. So what we wanted to know is whether our hypothesis of this second robot learning faster actually holds. And maybe look at this peg insertion problem first. So here you see the learning curve when this fixture is placed optimally or not. Basically, the learning curves in orange is when the fixture is in exactly the right place, and you can see that the speed at which this other robot learns is very high. If you place it in a suboptimal way, if there's no fixture, it's very hard to learn this task, and you basically need a lot of samples to do it. And similarly, we have similar results for the other task, basically. Okay, so also just to give you an intuition, this is how the Q map looks like for this fixture pose selection. So here you have, for one fixed orientation of this fixture, you see the X and the Y positioning of this. And you see at this particular orientation where these two corners are constrained, you get the highest Q value. So the other robot learns the fastest to insert it. And the same holds true for the other orientations as well. So how does this then look like at test time? So here we have the helper robot, basically sampling a bunch of hypotheses of how to place this fixture. We use Qt-opt, basically, to home in on this. And then we have the other robot basically executing that learned policy. This is a different manipulation task where we place this constraint so that this wrench is not moving up and down, right? So it also becomes much easier to turn the screw. And we have the shallow depth insertion as well, where the robot figures out how to best place it. And this is actually a more complex task where the robot then also has to slide, kind of slide away from this without basically removing the battery again. Okay, so just to summarize this particular one of the three ideas. So basically, the main idea here was that instead of trying to become better at perception and trying to increase or decrease the uncertainty about where this particular hole is, we thought, okay, how about we place fixture in the environment so that the uncertainty in the manipulation task is funneled to something smaller. And what we found is actually that this helps dramatically speeds up the learning curve or the learning process for the learner robot. And we had an algorithmic contribution here where we proposed a smooth zooming algorithm for learning a discontinuous Q-function. And as I said, the learning is basically sped up for the inner loop robot. Okay, so again, so that was one of the three example projects that I wanted to talk about, that instead of trying to explicitly decrease uncertainty through, for example, improving perception, we actually manipulate the environment to funnel uncertainty. Then another one of the projects I want to talk about also deals with the uncertainty, but this time it's about the dynamics of the scene, okay? So, and specifically, we're looking at the problem of task and motion planning. So what we have here is one of our robots. Its task is to actually move this cube that is outside of the workspace of the robot onto the shelf. And it basically has to figure out that it has to use this hook or this tool to get this closer. So what is required is some symbolic reasoning and then also some geometric reasoning to figure out the trajectory. So this is what we want the robot to figure out, actually. Now there has been work on this before that combines symbolic and geometric reasoning, especially with trajectory optimization. But we wondered really, how can we actually bring that kind of work onto a real robot where there is uncertainty through perception, but also things might be moving around? How can we deal with this? So here you see that obviously the robot is being annoyed by someone, Toki in this case, perturbing the environment. So what we basically wanted to achieve is a framework in which the plans basically stay valid despite the environment changing. And this is basically the overall approach that we took. So we adopted the approach from Marc Toussaint's paper from RSS 2018, where he uses something called logic geometric programming. And let me just walk you through this optimization problem. You basically, on the top, have a trajectory optimization problem, where you want to figure out basically the robot commands, but also the symbolic actions, a skeleton, basically. And you have a terminal cost here, and this is just a typical trajectory optimization cost that you want to optimize over. And then you have a bunch of constraints. So for example, these ones are just the continuous dynamics of the robot that are conditioned on the particular symbolic state that the robot is currently in. And you also have the instantaneous dynamics when the discrete action actually changes, right? And here are some constraints about the logic constraints about basically how you switch from one symbolic state to the other given a symbolic action. Okay, so that's the kind of problem we try to solve. And specifically, we want to solve it such that it's that whatever we figure out here, whatever the optimal solution is, stays intact or valid, even though the environment changes. And for figuring out the symbolic action, we basically stick to strips planning, where we define a bunch of symbolic actions that have preconditions and postconditions. And we have a bunch of symbolic states, initial states and goal states. And then really we just do this kind of logic planning using a tree that looks like this. So it's really just like in previous work. The problem is that the strips planner might be coming up with a valid symbolic plan that is not achievable by the robot, right? So on top of this symbolic plan, we also want to understand the trajectory that the robot actually has to go through. And in Marc Toussaint's paper, he formulated this trajectory optimization in joint space and even augmented the joint space with a potential object that the robot has grasped. So you see like this trajectory optimization problem and this continuous dynamics and the instantaneous switching dynamics. So the problem with this approach, though, is so first of all, this overall problem is nice because you can basically sum the trajectory cost across all time steps, and it results in a bandit Hessian, and then you can efficiently invert it with the Gauss-Newton method. But the annoying things here are these constraints that are actually depend on the entire trajectory and couple basically the constraints over the entire trajectory. And that makes the Jacobian actually quite complex. So for example, the way this robot grasps the object and how it ends up in the hand will then, if you optimize in joints, influence what the joints should be like, or the trajectory in joint space should be like relative to this box that you want to place it on, right? So that's kind of the problem. So the way we reformulated this problem to make it actually be able to cope with dynamic changes is to, instead of optimizing in joint space, we optimize a sequence of Cartesian frames that we define relative to the target object. So, for example, in this first step of our logic plan, we want the robot to pick up this box, right? And therefore, we control the end effector frame, and the target is the box frame, right? So that's fine. And then, perception and robotics happens, and actually, this box is going to be kind of awkwardly positioned in this hand, maybe not perfectly in the same way. and we still want to be able to place this box nicely onto the shelf. Basically what we do is we define these relative frames where it doesn't really matter how exactly the box has been grasped by the manipulator. We just care about controlling the frame of this box relative to the frame of this target object, which is the shelf. Okay. Okay, so, and by doing this reformulation, we switch basically from this joint space formulation to a formulation where we figure out a bunch of keyframes of relative Cartesian frames, and then these constraints become decoupled in time. So you see they're not anymore over all the time steps. Instead, we put a lot of complexity in the objective function. But basically, this becomes way easier to derive for all the different primitive actions. OK. And so the nice thing here is now these relative Cartesian frames, even if the object moves, that's fine, right? Because I'm still defining everything relative to even this moving object. So this logic plan just stays valid. Also, we use just an operational space controller to actually make the robot go to these particular things. We don't actually optimize the entire trajectory. And therefore, we can continuously adapt to whatever is moving around. And because of this reformulation, we basically have the following system, where basically we have a planning part that has a symbolic planner that produces some kind of action skeleton that is symbolically fine, you know, like valid. And then we send that symbolic frame to the execution side that actually optimizes these Cartesian frames. And then we basically just have an operational space controller that actually executes this, right? And one of the things that actually is not yet happening are these arrows. So I forgot to make a cross here. So we haven't yet figured out, like, oh, when can you actually change your plan or be more efficient if the environment changes. But I just want to show you what we have right now. So this is, for example, one of the plans, one of two valid plans that this whole framework produces, plus the motion of the robot. So the Tower of Hanoi, obviously. And one of the things you see is we don't yet have collision avoidance between the objects. So, you know, there's only so many hours a day. But yeah, so that would be also the next step. And I already shown you this video where, you know, we have a plan that wants to use this hook to get this one closer. And you see how this action skeleton from the strips planner basically stays valid. And because we use an operational space controller that just goes to this frame that is defined relative to these moving objects, everything stays still valid. And of course, I always like when things work on an actual robot. So here we made this whole framework work on a robot. We were actually combining some model-based perception for visual tracking all of these objects with some markers to make it robust. So that's also another future direction. And then we show how this actually works in the real world with Choki here basically being annoying to the robot. Yeah. So you see this is not sped up or anything. This is also in real time. And also there's no learning in this framework, just to say that. Okay. Okay, so this was the second work I wanted to talk about. So basically the main idea was here to solve task and motion planning for dynamic, or the main problem was to solve task and motion planning for dynamic environments. And the main idea is that instead of optimizing in joint space, we want to optimize over relative Cartesian frames, and we reformulated this trajectory optimization problem accordingly. And so I've shown you some examples of what it can do despite the environment changing. And yeah, so as a third project, I wanted to talk about another manipulation problem, which is the manipulation of deformable objects. And so I just going to show you first what we wanted to achieve. So we basically have a goal image of a particular rope. Sorry for this bad quality, actually. That is like of some kind of rope with particular appearance. And now the robot's task is to really just basically take its own rope and bring it as close as possible into this space. So what is the challenge here? There are multiple sources of uncertainty. One is in perception. So we really wanted to have a method that is able to work with all of these different complex possible situations of a rope on a different background occluded by the robot while it's manipulating with some distractor objects. I don't know what's so difficult here, no idea. This is in Berkeley, just, you know, your data set, I guess. We also wanted to make sure it works with all of these different, we got a lot of reviewers' comments, so we tried to include as many complex possible scenarios we can to convince people that this actually works. There are multiple ropes here. And yeah, we want to make sure that in all of these different cases, the method actually gives a reasonable estimate of the state, varying appearance and with occlusions. So also, another source of uncertainty in this problem is the dynamics of this particular rope. So depending on the particular material and a particular action, there might be many different ways on how this particular rope is actually evolving and deforming over time, right? It's very complex. And I think we do have actually models for simulating all of these things, but they're very computationally intensive unless you make a lot of approximations. So we have all these different sources of uncertainty. So what does that mean? That basically means that as soon as the robot goes in and tries to get this rope into the shape it wants, something that it hasn't expected is actually going to happen, right? And to combat this, basically we took an approach that, again, caters to a planner that is actually fast enough to continuously replan. So in particular here we use MPPI, so Model Predictive Path Integral Control, I think. And it's basically an MPC method that relies on a dynamics model and then just tries to basically optimize over a horizon and can continuously replan. So that's basically the method that we want to use to whatever the MPC method is, really. But we want to use MPC that takes in this goal image and then can continuously replan to cope with all this uncertainty. And the particular problem here is really that we addressed in this particular work is how to perceive this high-dimensional state space. And this is really what I want to talk about in this part. The main contribution here is really this differentiable renderer that we came up with. So we basically get an input image. Again, it's from Berkeley. And we feed it into our perception network that has also some technical detail that I'm not going to talk about today. And given this perception network, we basically get the output of this rope state. And given this particular rope state, we can actually render basically the foreground and the background given this information or given this estimated state. And from this rendered state, we can form a Gaussian mixture model, one Gaussian for the foreground, one for the background, and then compute the weights, the per pixel weights, given this particular GMM, right? So this image just says like, okay, given my particular RGB model here, how likely is this pixel belong to the foreground or to the background? Okay, so given this, given these two images, like one coming from this renderer, given the estimated state, and one coming from the GMM model, we can actually compare these two images and compute a loss over this and how different they are. And now, given this, this loss or this difference between these two images, we can do two of the following things. We can either backpropagate this error to actually change the, to basically adapt the state to fine-tune it to be closer to this. Or we can even fine-tune the perception network if we have a bunch of maybe example data that a robot would have. So I also want to say that this particular model, it actually doesn't assume a particular foreground or background model. You remember there were all these different appearances that we used. And the reason for this is that this particular GMM model, it's not like given or anything. It's it has basically transient parameters that are changing in the particular appearance of this particular scene. And really this is how we can achieve a really good state estimation despite all of these kind of distractors in the scene. So here I already showed you these last rows here before, which is actually the output of our model for a particular scene. And keep in mind, like this is using all the same model, right? And we compared with an L2 loss. And this is just a manual initialization. And you see it can deal with very different challenges, basically. And we also, my computer is going to shut down. Running out of power. Okay. We can also deal with intersections, and it also works with that. We also use actually tracking over time, which I haven't talked about. Because of exploiting temporal consistency, we can also track where exactly this intersection happens. So yeah, and given all this, this is basically the system that we achieve, where we give the robot basically this goal image. This is with a rope of whatever kind. You can even use gentle floss, I think, as long as the contrast between the foreground and the background is high enough. That's the assumption we make. And so really the robot can basically move this rope. Maybe one thing you can also see is that we use this particular, what it has to do here is also to predict, given the dynamics forward, what the sequence of action will do. And you can see that it sometimes really uses this weird dynamics of the rope where pulling here will also move this part of the rope. Right? I think there are a few examples of this here. All right, so just to summarize this particular part of the talk. So we wanted to do deformable object manipulation for now, basically moving this rope into a particular goal state on the plane. And the main idea that we did here, which is maybe not so special, is really that we decided we're going to represent this rope in just a normal state space. You know, it's just X, Y, Z position of these nodes. And the reason why this is nice is because you can easily incorporate physics priors into this problem because it's a meaningful representation. You can also do easy planning, easy distance computation of the distance. But what is hard is, of course, perceiving the state, which is very high dimensionable. And this is where we propose a differentiable renderer for also self-supervised learning and robust state estimation. And what I showed you was a system for manipulating deformable objects into this given goal state. So yeah, so with this, I basically showed you these 3 example projects. And in which we really, I think, embraced uncertainty by just accepting it and trying to deal with it explicitly. So the uncertainty in these different problems came mainly through perception, but also noise and execution. Every robot you're going to touch is not going to do exactly what you wanted it to do. There might be a dynamically changing scene, and there might be uncertain dynamics model as well. And so what did we do here? So in the first project, we eased execution by actually placing physical fixtures in the scene, and one robot learned to help the other robot. In the middle project, we reformulated an optimization problem to allow real-time adaptation of a particular plan. And also in this last project on the manipulation of deformable objects, we basically enabled continuous feedback on the state space model of this rope to allow fast replanning. And yeah, so I think in robotics, one way to look at this problem is to maybe not try to achieve the impossible, which is perfect accuracy in scene understanding and prediction, but think about approaches that would deal with the ever-remaining uncertainty that you have through either replanning or maybe funneling it through changing the environment. So thank you very much that you came, despite the ICML deadline. And these are all the amazing students who are working with me and who have done all the work. Thank you. Are there any questions?
Yes, one of the things that is very interesting is this moving objects and the fact that you can take care of it. But I assume there are limits, right? So if I move it like speed of light, or I take it down from there, you will not be able to.
Yes.
So is there some guarantee or some bounds of what you can achieve with your technique with respect to movement?
I mean, there are the physical constraints that you mentioned. So if it's not in the workspace of the robot anymore, right, it's basically an infeasible problem to solve. Then are there any bounds? So one of the things...
because you are doing a sort of adaptive control on the fly, in which
so you can...
There is an invariant, which is a logic flying.
Yeah. That one stays invariant. The Cartesian frames, they move, but they...
How much can they move?
Yeah.
To guarantee that you are actually
Right.
in the goal.
So I think it's mostly, the limits are mostly determined by the workspace of the robot here. So you can always move the objects around so that they end up leading the robot through some singularity that make it basically go unstable potentially. So we haven't put any safety constraints on. You're just talking to all the students from Claire Tomlin, for example. So we haven't actually looked at any of this, but that would be very useful. So there are right now no guarantees really on it. And also no, as I said, there are two of these errors that we actually didn't implement them that go back from the current state of the scene and tell maybe either the trajectory optimizer or things actually need to change here, or you really need to replan because otherwise your reactive controller that has no look ahead is just going to end up in some local minima. Yeah, so that we haven't done and it's still missing. Yeah.
Because I mean, the interesting thing is that there is not really learning in it. So there are deterministic algorithms that take place and all that. So the frame should be amenable to demonstrate what you can do and what you can't do.
Yeah.
Which in other cases in learning, who knows, right?
Yeah.
Going and offer the best, right?
Yeah.
So your approach is definitely interesting, but without these limits, it's difficult to assess.
Yeah, I completely agree with that. Maybe one of the things that I like about learning for this particular problem, or where I think that could be an interesting part is, let me see. So right now, I haven't actually shown this, but all of these actions that we are defining here, they're all easily defined in terms of preconditions, postconditions. But what is really painful is to derive the constraints that are on the Jacobians that are actually plugged into the optimization problem. They're easier than for the other approach in joint space, but they are still very painful. So it's very difficult to scale this up, essentially to add more of these kinds of actions. And I'm wondering, one of the things we're wondering about is basically, is there a way to maybe learn these constraints from, I don't know, from data that is out there? I don't know what the effect is going to be on removing some of the nice potential guarantees that we have, but what it would help with is potentially to scale up this number of actions that are here, I think.
essentially wish it away or sense it away. I'm curious about the aspect of learning in the context of actually all the projects. In particular, say the first one, you find this angle, right, that, or the placement. There's sort of an implicit assumption that one of the robots is actually precise and the other one isn't, right? Because you can go back. It can place the fixture accurately over and over again, right?
Yeah.
During iterations. Okay.
Yeah.
So I'm just wondering, what if you introduce uncertainty in that as well? In other words, if you have uncertainty in the fixture placement, it's still learning a strategy
Yeah.
that's actually robust.
Right. So, so first of all, we did this on a real robot, right? So definitely the uncertainty that this very crappy Canova robot has is we already have to deal with it, and yeah, I don't. So we didn't really explicitly include it, but also, I guess if I showed this Q function again. Right? So even if we are covering this whole, okay, that's not going to work very well, right? The other robot is never going to learn. But there is some slack here. Also, there is some, here, for example, we have not this perfect alignment, right? But there are constraints through these two points. So there are multiple solutions that are at least helping and not preventing it. So there's some slack there. Another thing that I haven't shown that we did here as well is, you know, if you actually teach your kid how to ride a bike, if you use training wheels, at some point you want to take them away, right? And what is going to happen is your kid is going to fall over, I think. So the same happens here, right? So if we take this policy that the inner loop robot has learned and replay it without the fixture, so we take the fixture away, then this is basically the amount of time it needs to somehow now learn without the fixture, right? Like try to reproduce that skill. And it really takes some time. So what we also did was to say, okay, what about instead of having the physical fixture there, we're just going to have a potential field that that is of the same shape as this fixture and use that to constrain somehow the motion of this. And that actually, this is the green curve here, and that actually also works quite well. So that could be also an interesting idea to explore further. Like how can you maybe do this with virtual fixtures instead of having an actual robot, kind of expensive. That could be another way. Also, another thing here is that we, of course, we hand design the fixtures, right? We knew exactly, okay, these are the right fixtures for these tasks. That could be also an interesting problem to search for. Like, what is the geometry of the fixtures or of the environment that we want to change to constrain this? But yeah, so just to answer your question, like rolling back, I think there are like multiple solutions that help. And even if we take the fixture away, by keeping it with a soft potential field, we can still kind of exploit this policy that was learned with the physical fixtures. Yeah.
I'm going to ask questions that some students may expect from me. What is the value of learning?
Like in general, or
In this particular case,
in this?
can you show that having learned a skill, you can take now all the learned parameters and repeat the whole action much faster or more reliable? What's the value of the learning?
If I can do the learned policy faster, or then what compared to what?
Well, I mean, you have spent here considerable time on learning how to do it, right?
Yes.
Okay. So, given that you have learned it, you learn certain parameters of the task.
Yeah.
as a prior, what's the benefit?
Okay.
Can you do it faster? Can you do it more reliably?
Yeah. So, okay, so let's take the peg insertion task. And now I really regret to have forgotten one of the slides that I really should have added here. Let me see if I... okay. So this is from a different presentation, and I have forgotten to include this, but this is basically taking the same policy that we learned on the rectangular peg without knowing anything about this geometry, that it's rectangular, taking it, using the same fixture pose, and then executing it with a differently shaped peg. So
Did you extract the round, the geometry? Or?
we gave it basically. So what we did is we gave.
What are you getting out?
I'm getting out of this that, so I could do the following. I could try to solve peg insertion in like in the way where I'm saying like I do model-based tracking of this particular hole, right? And I'm gonna do model-based tracking of this peg, and I could do that, and then I could just have a yes, exactly, yes. And I haven't talked about the project we did on four-stroke measurements here. It's actually not used in this project. But I could do this, but the assumption that I make there is that I know the geometry, exactly the geometry of the problem, right? I know the CAD models of the cylindrical peg or of this triangular peg, or right. If I want to do it in this model-based way, what I gain with the learning-based approach is that I don't have to assume that. So what we've shown is actually we can take the policy that was learned on the rectangular peg and apply the same thing on the round and on these.
What are the variables?
Say again?
In the policy, what is underneath? What are the variables?
So for the inner loop, it's a 2-layer neural network.
I see.
Yes. Yes.
I'm just curious, but just follow up on that, because you can't get a square peg into a round hole, right?
Yes, that's true. So these are actually having these are having round holes. Yeah, but it happens that this fixture works also for all these different pegs, right?
But what does that look like actually? Because you have a video of just, I'm curious, what is it? It's a learned policy of kind of gathering the position in a certain kind of way, or
Let me check this. Like,
So when you are storing that neural net, you are basically taking a lot of memory as opposed to compressed
yes,
variables.
I agree with that.
That's the trade-off.
Yes, I agree with that. Yeah, I do save the geometry on the CAD models, though. I don't exactly know how they now compare, but yeah. So I do have a video. Let me see if I can. Let's see if this shows up here. No, it doesn't. Ugh, sorry. I wasn't planning to show this one, so that's why it doesn't work.
But just intuition. Jeannette,
Yeah.
You run out like 5,000 iterations or so, right?
Yeah,
So,
in simulation actually, and yeah.
So what does it look like though? Is it a pretty fast sort of process, or it gets better over time? So what is it?
Say again. The last one was what?
What is it doing? I mean, what does it look like, the final policy?
It's basically the final one I think I showed. So let's look at this again. It's basically doing this sliding and wiggling in, right? So this is just a part where the other robot tries to figure out where to best place the fixture, right, from the learned Q-function. Does Qt op, blah, blah, blah. Okay. So what happens, I think, is it's just going to push against this and really exploits that resistance, right? Yeah.
So when you do it with your robot, do you use the policy trains on simulation?
Yes.
Do you have to fine-tune it?
No. Which was surprising, but yeah, we didn't.
When you transfer to the differently shaped pegs and holes, do do you use the same policy or do you do some relearning of
The
the
same.
task?
Because it basically exploit, so we did it only for the PEG zone, not for this shallow depth insertion and stuff. But for the PEGs, I mean, it's really, I think, just trying to place position maybe inside of the fixture, like impedance control, and then just exploits this constraint, and just happens to be, for the round PEG, it's just the same contact points, right, that it exploits there.
So you talked at the beginning about like your I don't know, ideal situation would be like to understand the security gradient of like how humans do this. But like little kids like are able to do this, hopefully, like they fiddle around with it, but they don't actually need these like tools or scaffolding like help with this kind of similar tasks. So like
That's true.
kind of how,
Yeah.
I don't know, I guess what's your opinion?
Right, they don't need it with maybe the similar tasks, but maybe they have like larger tolerance, you know, they start with like more easy tasks. But there are certain tasks where kids are using scaffolding. It's not always physical, sometimes it's just, I think it's actually a term in developmental psychology, where scaffolding is used for learning, and it can be verbal, or it can also be kinesthetic or something like this. Or I think there are even like some sports are being learned with physical constraints as well. Now, I don't know if you have I forgot which one it was, but so some of these things are just easier to learn. But I agree with you, some of these play things, they, that you see in kids, they don't really need these kinds of scaffolds. I think it's just maybe a combination of inbuilt priors and just figuring things out and doing experiments. Yeah, I mean, I don't know. I'm not a cognitive psychologist, so I'm really out of my depth here.
Just an example is like for people, weightlifters or things, they tend to wear things that
Right.
fit their body in a certain way, and then
Yeah.
they learn how to avoid straining, right? So and the bicycle wheels, training wheels, is a beautiful example.
Yeah, I was just kind of wondering more like, this is like a simpler task.
Yeah.
Training on bicycles, so I was wondering like what's, you know, do you think there's some sort of like level of task where like humans can do it like, kind of without scaffolding, and then at some point they need it, and like,
Yeah.
hopefully keep that with their lives?
Yeah, it's a very good, it's a very good question. I mean, clearly robots are way behind.